Let's go ahead and we're going to talk about scatter plots and lines of best fit, and that would be section 2.6. Scatter plots can be classified in three main types of categories. You have your positive correlation when you were to plot points of data like so. It would create kind of a positive slope, in a sense. Not exactly a line, but it seems to be, the general trend seems to be in that direction. Something like that would be, for instance, if you're comparing the amount of time you spend shopping and the amount of money you end up spending, for example, or maybe the amount of time spent studying and your grade, generally speaking. If it has a negative trend, the the data points tend to head down. For instance, the further you drive, the amount of gas you have would go down if you were to plot that sort of data, and that would have a negative correlation. Um, and if the dots are just your data points are just all over the place, then that's going to be, we would say approximately no correlation. For instance, something with no correlation would be the amount of time you spend brushing your teeth and how fast you run. There's no correlation between those two. So if you were to plot those data points, you would it would just be a big blotch. You won't see any trend. There's also a thing called a correlation coefficient. And what a correlation coefficient is basically how well the points match your graph. So, for instance, um, if I were to have a graph with with a number of points, let's say, you know, something like this, I would say that has a very strong positive correlation. And our correlation coefficient can range between -1 and 1. Well, if it's a strong positive correlation, I would, if it's like practically a perfect line, I'd give this a R value, which we use for correlation coefficient, of 1. So R would be 1. But let's say these points go down. So for instance, they do something like this. Almost a perfectly straight line but headed in the opposite direction. Well then our R value would be -1. So on the left hand we have the lowest the R value can be -1, and that's a very strong negative correlation. But on the other end of the spectrum, we have a very strong positive correlation with R equal +1. And if we have a graph in which we can't really tell, if it basically has no correlation, so let's say our data points, are just all over the place, then we say it has no correlation, and therefore our R value would be 0. Okay, so we have R equals 1 for a strong positive, R equals -1 for a strong negative correlation. But there are degrees in between. So for instance, let's say my points head in a positive direction, but it's not, it's not like a perfectly straight line. So we'd have something like this. I mean, I can see that it has a positive trend, but the points are, not, in a straight line. Well, then I would estimate my R value as, well, it's positive, but it's not like super strong. So maybe I'd give this an R value of 0.5. It's a loose association, but it's still, you can clearly see it has a positive trend to it. And if it was a loose association but headed downward, then our R value or correlation coefficient would be let's say, negative 0.5. So here's an example. We want to tell whether the correlation coefficient for this data is closest to -1, -0.5, 0, 0.5, or 1. And I can see that the points here are fairly strong in this region here. And we have a couple points here and here which aren't exactly in line, but the majority of the points seem to be heading down. So it's going to tell me that my R value, my correlation coefficient, is going to be a negative number. I would estimate this to be maybe a correlation coefficient of maybe 0.9 or something. It wouldn't be exactly a 1, a negative 0.9. So given our options, negative 0.9 is going to be closest to -1. So I'd say my correlation coefficient here is closest to -1. And it's kind of a subjective thing. You just kind of have to look at it and judge it based off your experiences at looking at other graphs. So anyway, that's a correlation coefficient for you. Now let's look at a second example. Here we have a table that gives systolic blood pressure Y of patients X years old. We want to determine the correlation coefficient, then approximate the best fitting line for the data. Okay, now let's say we want an exact correlation coefficient. We don't want to estimate it by just looking at the points. We can actually enter this data into our calculators and get it, the calculator has an algorithm which will determine the exact correlation coefficient. So here's how you do that. First, you have to turn on your calculator's ability to determine what R is, the correlation coefficient. To do that, and you're going to want to write this down how to do it. First, you have to turn it on, and we're going to press second and 0. This will take us into the catalog of all the different functions on the calculator. And what I want to do, there's an alpha, an A in the upper right hand corner of the screen. That means it's in alpha mode. That'll help us jump down to what we want. And right here on x minus x to the -1 power, there's a D. We want to go hit D. And then we're going to scroll down. And what we're looking for is diagnostics on. And here we have diagnostics off and diagnostics on. I want diagnostics on, so I'm going to press enter. And now it's on your main screen, and I'm just going to press enter again. Now your diagnostics are on. You only have to do this once, okay? Once you turn it on, it stays on unless you reset your calculator. Then you might have to go back and turn it on. Now we need to enter the data points. So this is dealing with statistics, and we're going to input a list of data. So we're going to press second and stat. And here we see we have the names of the list, L1, L2, and so forth. We're going to edit one of the lists. To do that, which is L1 in this case, we're just going to go ahead and hit stat. All right, I'm just showing you the L1, L2 where you find that. I'm going to press stat, and I want to edit one of the lists. So I press enter. Okay, now you might have data already in your calculator. To clear that out, what you're going to do is you're going to hit the up arrow and highlight one of the lists. So here I'm highlighting L2, and I'm going to hit clear, and then enter. That clears out that list. And then I'm going to arrow to the left and highlight L1, hit clear, and press enter. Do not hit delete when you have the list. Otherwise, you're going to delete the whole list, and then you have to figure out how you put the list back. All right, so let's enter our data. I'm going to make L1 my X values. The X is going to be the age. And So let's see, I'm going to have 43, 48. And if you make a mistake, you can just simply highlight it like I did there and retype it in, and then it'll change it. 56, 61, 67, and 70. Then I'm going to arrow over to list 2 and enter the systolic pressure, which is the pressure when your heart compresses. You have diastolic and systolic. And the systolic is when your heart actually pumps, your pressure goes up, as opposed to diastolic where it's just at rest, between pumps, if you will. Okay, 143, 141, and 152. Enter. Okay, so we've entered that data into our list. And now I'm just going to quit out of this. Second, quit. And then I'm going to go under my stats, and I'm going to arrow to the right to calc. And we're going to do a thing called a linear regression. Our linear regression, it's going to come up with an exact calculation of what the best fit line is. Now you still have to be able to do that by hand. I'm going to show you how you do that by hand, but the calculator does do that. In the linear regression, it's y equals ax plus b, and it's saying, okay, well, a is 1, b is 81. Our r value here is, and this is what I really want to point out, our r value is 1. Which the calculator is saying, hey, this is a really strong relationship in the positive direction, so a very positive slope. So when we plot these points, it should look something like that. So our r value, we said, is equal to 1. Okay, so we have that, and that's an exact one using the calculator. Now let's come up with a line of best fit by hand. So we'll start plotting these points, and let's see, we have x is 43 and y is 128. So we're going to go to 43. I've set up my table to count on the x counting by 5s, and on the y it's counting by 10s. Let's see, so 43 is going to be about here, and then we want to bring it up to 128. So I would approximate that's just going to be a shade below 130, and this is going to be a shade to the right of 40. So about here. And let's see, 120 and 48. So 48. Just a shade left of 50, and 120 is going to be right on that line for 120. 56 and 135, so this is 55, so almost on the line for 55, just a bit to the right of it. And 35, that's going to be halfway between 130 and 140. And 61 and 143, so 61 and 143, so 143 is going to, so this is 140, so 143 is going to be about here. And 67 and 141, so about here. And finally 70 and 152, so it's going to be just a bit off the graph here. I didn't make a very good graph because it doesn't contain all the points here, but I had limited space. That's my excuse. Anyway, All right, so we have our points, and we can see they're pretty strong, strong enough for our calculator to term this as a positive correlation coefficient of 1. And see, it is a positive, and we see this has an upward trend to it. Now, when we draw our line of best fit, here are the rules that we try to abide by. We want to pick, we want to try to get as many points above the line as below the line. And then we want the line to try to go through 2 points that are, are fairly far apart. We don't want to get it to go through points that are right next to each other. So again, this is kind of a subjective thing, and you get better with it the more practice you have with it. So if I were to do this, and well, I am going to do this, I would see that I have like three points in a row here. So I can hit quite a few points here. You also want to try to go through as many points as possible. And I have 2 points that are fairly far apart. And then by doing this, I'm going to have a couple points below it and 1 point above. So I'll have almost the same number of points above as below. And so, but I have to go through at least 2 points, at least through 2 points. And so I'll say that would be my line. I'm going to put in my arrow. The points that I'm going through, it's important that I pick 2 points that are far, the furthest distance apart on my line that I drew. So that would be this point and this point. That means we're going to use the point 70, 152, and it looks like the other point's going to be 56, 135. So this one. And we're going to use those 2 points to come up with the equation for our best fitting line. And then we'll see how we did compared to what the calculator is. Okay, so we said that the points were the 70 and 152 and the 56 and 135. So let's set this up. I have, I'm going to write these as ordered pairs, 56, 135. And this is just like finding a line that goes through 2 points. So the first thing we want to do is find a slope, and then we can use point slope form to come up with that equation. So remember, slope A or M is going to be y2 minus y sub 1 over x sub 2 minus x sub 1. I'm going to call this x sub 1, y sub 1, x sub 2, and y sub 2. So it's going to be 152 minus 135 divided by 70 minus 56. Okay, so that's going to give us 17 over 14. So that would be approximately 1.2. So we have our slope, 1.2. Now we're going to use the point slope form, y minus y sub 1 is equal to a times x minus x sub 1. I'm going to go ahead and use the 56 and 135. So y minus 135 is equal to 1.2 times, and then x minus 56. I'll distribute the 1.2. 1.2x minus 67.2. And then we're going to add 35 to both sides. So say plus 135 plus 135. So y equals 1.2x, and let's see, that's going to give us 67.8. So plus 67.8. So that would be the equation of our best fit line. And we can do that by hand. So is it exact? Is it the best one? I don't know. But it's pretty, I think it's pretty close, for the most part. And we have, you might do this, several times, or find slightly different lines, and you can average them to get a better line of best fit or equation. But for our purposes, this will be good enough. Okay, so that concludes our lesson on scatter plots and lines of best fit, and I hope that helped.